In this video, we're going to focus on graphical summaries of data where we're dealing with quantitative data. The actual kind of corresponding section in the textbook is actually called frequency distributions and their graphs, but I think a better way to think of it is it's really the same as what we were doing in the last section where we were looking at graphical summaries of data and we focused on qualitative data. Really all we're doing here is changing it so the focus is on quantitative data. So, I mentioned in the last video that we have to treat quantitative data a little bit differently than we treat qualitative data, hence covering it in two different sections here. So, how so? First, I want to think about how we dealt with qualitative data in the last section. The first thing that we did to visualize qualitative data was to create a frequency distribution. That was the table where we put in our different categories and the frequency with which those categories occurred. What we were doing when we created those tables was taking a list of qualitative data, right? Chocolate, vanilla, strawberry, the flavors of the ice cream that we were dealing with, and we were converting them to quantitative data. We were talking about their frequency: 43 chocolates, 30 strawberries, 27 vanillas out of the 100 ice cream orders. So when we were dealing with qualitative data, we had to convert it to quantitative data before we could start doing math stuff with it, which makes sense, right? To do all these graphs, these things that involve numbers, we had to go from categories to numbers. In this case, we're starting with quantitative data, so the data already involves numbers. And you might suspect that this means that it's actually going to be easier to deal with this type of data. If our data is quantitative to begin with, then maybe we don't have to do the conversion process like we did when we were dealing with qualitative data, where we have to convert it into numbers. This is already numbers. And it turns out that's actually not quite the case. Dealing with quantitative data is actually a little bit more difficult than dealing with qualitative data when it comes to doing graphical summaries. So let me illustrate why this is. So let me just write this down. Quantitative data typically requires an extra step. To create the graphical summaries that we're interested in. And again, graphical summaries is just sort of a broad way of saying both the tables and the graphs that we've been talking about. Graphical. Sorry, my handwriting with this new touchpad here I got is not very great. To create graphical summaries. Okay, so quantitative data requires an extra step to create our graphical summaries, and we can see that in the following example. Let's say I want to record the exam scores of the 30 people that are enrolled in this class. So let's talk about the exam scores of the 30 people in class. My exams are out of 100 points. The lowest score you can get is a 0. Typically that's only if you don't show up at all. And the best score you can get is 100, but you can also get any point value in between, right? You can get a 1 or a 2 or a 3 or a 4 or a 75 or a 83 or a 92 or whatever. You can get any one of those numbers. So if I've got my list of scores, if we have a list of scores in no particular order, maybe I will do them in order. So maybe somebody didn't show up, there was a 0. And then somebody bombed it and they got a 34. And then the next worst score was maybe a 57. And then there was a 60. And then, dot, dot, dot. Maybe there was some scores in the 70s. There was a 72, another 72, maybe a 75, dot, 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 dot. And then there were some scores up in, I don't know, in the 90s. Maybe somebody got a 97. And maybe one person got 99. That was our high score. So we've got this big long list of scores. Imagine now that I want to create a bar graph of these things. Well, if you think about it, I want to keep track of sort of our frequency distribution, but the categories are now the individual scores that people got. And if you look at the list of possible scores from 0 to 100, there are actually, because of the 0, there's actually 101 possible scores that somebody could get. So our bar graph is going to look something like this. Here's going to be the frequency, and this is going to be where our categories are, but I actually need to make this line much longer and probably basically off the page that way. So these would be the scores, right? The exam scores. And the low score would be a 0, then maybe a 1, and a 2, and a 3, and I'll do some dot dot dots here. We'll get into the 30, so there's a 33, 34, 35. I've got to list every possible exam score. Let's go back, whatever, up into the 50s, 56, 57, 58, 59, 60, 61, all the way into the 70s, 72, 73, 74, 75, dot, 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 97, 98, 99, and 100. And even with all the dot, dot, dots, skipping the vast majority of numbers, this graph is already starting to look absurd. And then when we look at the frequencies, we're counting up how many people got each one of these scores. So how many people got a 0? Well, it turns out there was one person that got a 0. So there's my bar graph, my one person that got a 0. How many people scored a 1? Nobody. How many people scored a 2? Nobody. How many people scored a 3? Nobody. And in fact, the vast majority of the bars are going to be missing, right? Because if there's 101 possible scores that you could get on an exam, but there's only 30 people in the class, then at most 70 of these, 71 of these, in fact, are going to be empty because there's not enough people to fill out this entire graph. So we said there was one person that got a 34, so there's my frequency of 1 there. What did we see? If somebody got a 57, then there's a bunch more zeros. Somebody got a 60, some more zeros. 2 people got a 72, so we finally have something that's a frequency greater than 1 or 0. Then nobody got a 73, nobody got a 74. One person got a 75, one person got a 97, one person got a 99. This is an ugly bar graph. It doesn't do or doesn't satisfy the fundamental purpose of a bar graph, which is to quickly display information. I would rather look at the list of numbers than look at this bar graph. I can draw more conclusions more quickly from a list of these 30 numbers than from this bar graph that has 100 possible values, a bunch of which are zeros. So this is basically a terrible graph. And this comes from just trying to directly graph this list of quantitative data that we've got. So we can't just do it directly. What we have to do instead is split our data basically up into categories. What we're basically going to do is take our quantitative data, convert it into, in a sense, qualitative data, basically put the values into categories, and then do the same process that we went through when we were dealing with qualitative data by looking at those categories and converting it back to quantitative data. So in section 2.1, when we were dealing with qualitative data, we had to do one step. We had to convert the qualitative data to quantitative data in order to graph it. Now that we're starting with quantitative data, more often than not, what we're going to have to do is go from quantitative data, numbers, to qualitative data, sort of categories, and then convert that data back to a different new version of the quantitative data. So numbers to categories and then back to numbers. It adds an extra step. So let me demonstrate how that would work. So we want to divide the data into classes. Classes are going to be the name of these categories that I was just talking about. So classes is the special name that we're going to use, which are basically, again, just sort of groups. So for example, a natural grouping when we're talking about exam grades would basically be letter grades, right? A's, B's, C's, and so on. But we want to set it up in such a way that our classes are each the same size. They each contain the same possible amount of stuff, the same possible range of values in a sense. So if you think about it, the way we break down letter grades, right? Scores in the 60s. Anything in the 60s, that's a D. Anything in the 70s, that's a C. Anything in the 80s, that's a B. Anything in the 90s, that's an A. Anything in the 50s or below is an F. But that means there's a lot more stuff, a lot more possible scores that are Fs. Anything from 0 all the way up to a 59 is an F. That means there's 60 possible scores you could get that would give you an F. But then there's only 10 from 60 to 69 that would give you a D. And that doesn't make sense. So we want to divide our data into classes of equal size. And so, in this case, based roughly on letter grades, we could pick the following setup. So maybe I pick all the scores from 0 to 9. So let me label this. My class is going to be right here, and I'll list them all out. So we'll have 0 to 9. That's one possible class, one possible grouping. 10 to 19, that's the next. 20 to 29, 30 to 39. And as I go through this, I'm being very consistent in making all these classes the same size. The word we're going to use for it is width. So they each have sort of, they span the same amount of numbers in this case. So 40 to 49, 50 to 59, 60 to 69, 70 to 79, 80 to 89, and 90 to 99. And notice I very conveniently left out the score of 100, which is also a possible score. We got lucky. Nobody scored a 100 here. The highest score was a 99. So we don't need to worry about that. But in general, we want all of our classes to be the same size. So if there had been a score of 100, we'd have to come up with a different way to kind of split up this data. Once I have these classes, now we can go back to kind of the process we were using before, where we then look at the frequency. So basically the question is, how many scores were there from 0 to 9? And in this case, based on the way I drew it, we said there was one. One person didn't show, and they got a 0. How many were in 10 to 19? Let's say there were 0. 20 to 29, there were also 0. The next lowest score, one person scored in the 30s. So there was one score in the 30s. And no scores in the 40s, and maybe it looks like one score in the 50s. I kind of skipped a bunch of the 60s, but let's say 60s. There were several scores. Maybe there's 6 people that scored in the 60s. Maybe 8 people scored in the 70s. 9 people scored in the 80s. And I need to check and see what I've got this to add up to so far. 1, 2, 3, plus 6 is 9. Plus this other 9 would be 18. Plus this 8 would be 26. So that leaves me with 4 people that scored in the 90s, maybe. So maybe this is what our frequency distribution looks like. And these are our so-called classes, and they're what we were calling kind of the categories. We grouped our numbers into these, you can think of them as bins, or again, the word that we're going to be using, the word that the textbook uses is classes. So little ranges of numbers split up in some semi-intuitive manner. And now the graph would look a lot more reasonable. We could convert this to a graph where we'd have basically the scores down here in the single digits, then the 10s, 20s, 30s, 40s, 50s, 60s, 70s, 80s, and 90s. We now have 10 categories. 10 categories is a much more reasonable number to have down here versus the 101 we had up in the original bar graph that was awful looking. So I'll put frequency here, and we can do this a number of ways. One common way is they'll just put some numbers down here and draw the bars sort of between them. So and you'll see what I mean hopefully in just a minute. So these are the scores down here. Oops. And it looks like the highest frequency that occurred was 9, so I need this to go up to at least 9. Let's count by 2s, 2, 4, 6, 8, 10. And we can see that we had, again, one score in this range, in the sort of 0 to 9. In the 10 to 19, there were none. In the 20 to 29, there were none. So I could kind of try to draw these a little more clearly. You can put some little hash marks where we're counting by our 10s down here. And now this will hopefully be more clear. So we had some 0 heights there. We had 1 in the 30 to 40 range. We had 1 in the, 0 in the 40 to 50 range. Sorry, 1 in the 30 to 40, 0 in the 40 to 50, 1 in the 50 to 60, went all the way up to 6 in the 60 to 70 range, or 60 to 69 range rather. And then 8 in the 70 to 79, 9, and then down to 4. And this graph gives you a much better sense of sort of the shape of our data. And that's the word I'll use a lot, shape. The shape of the data, you can kind of see where most people scored. You can see that there's these ones that are kind of stragglers off to one side. We'll eventually define these things as something called outliers. And we'll talk about how you determine if something's an outlier, but that'll be in chapter 3. So this is going to be our approach. This bar graph for our grouped quantitative data, right? We've grouped the data into our classes. Quantitative data is called a histogram. And this is going to be one of the main types of graphs that we'll actually be focusing on. Setting up exactly, going through the process we did here, setting up classes, counting the frequencies, and then creating the graph from there. So we can do this. Coming back to this, so here is our frequency distribution for our classes that we've set up. We could create this as a relative frequency distribution by just adding an additional column and computing the relative frequency by totaling all of our observations up and recognizing, oh, there's 30 observations, so the next one would be, this was relative frequency, you could add in that column, this would be 1 out of 30, and we could compute that as a decimal, 0 out of 30, and so on, 0 out of 30, 1 out of 30, just going through and taking each one of these numbers and dividing by 30. I'm going to undo that just for clarity's sake, but the point is it's the same procedure that we used in the previous section if we're trying to compute relative frequency and create a relative frequency distribution. The bar graph is again going to be called a histogram. So that's going to be important. It's possible that in our case, it's possible to pick different classes than the ones that we picked. we picked ours based on some sort of preconceived notion. We said, well, there's kind of a natural way to break up this data if it represents scores. We might kind of semi-correspond them to letter grades and think of A's, B's, C's, and so on, and then kind of do an F plus and an F and an F minus and an F minus minus and an F minus minus minus, and so on and so forth. Distinguish between good Fs and bad Fs so that we actually have all these different classes. But we didn't have to pick 10 classes. We could have done a bar graph where we only did 0 to 19 and 20 to 39 and 40 to 59 and 60 to 79 and 80 to 99 and broke it up into groups of spans of 20 numbers instead of spans of 10 numbers. So we have some choices when we pick our classes. And so let me give you a few definitions because this is going to be something. We'll need this language to discuss this concept of classes and how we can wind up actually creating some of these histograms. So let's see here. The first definition I want to give you is something called a lower class limit. And this is in contrast to another definition, before I actually define them, of an upper class limit. So the lower class limit of a class is just the smallest value in that class. And the upper class limit of a class is hopefully obviously going to be the largest value in that class. So if I take a look at our table here and I say, the top class down here, the 90 to 99 one, the lower class limit of this class is the 90. It's the smallest possible value you could have to fall into that class. The upper class limit is the 99. So it's just these two numbers. All the numbers on the right, they're all the upper class limits of all of these classes, and the numbers on the bottom are the lower class limit of each class. So again, if I look at this one here, the lower class limit is 20, the upper class limit is 29 of this particular class. We can use those to compute the class width, which is the size of the class. So the class width. The class width is going to be the difference between two consecutive lower class limits. Consecutive lower class limits. You could also do it as the difference between two successive or consecutive upper class limits. But the point is, in this example again, the class width is 10. Each of these basically span 10 possible values that you could get in there. So I can't compute the class width by just taking the upper class limit minus the lower class limit. So for example, if I look at this top class that I have written up here, if I took the upper class limit of 9 and subtract off the lower class limit of 0, I'd get 9 minus 0, which is only 9. That is not the class width. Instead, to get the 10, I need to subtract the 10, this lower class limit, from, subtract from this one, the one before it. So I can subtract 0 from 10, or I can subtract 10 from 20, or 20 from 30. And they give me the 10 that is the actual span of the amount of numbers that go into these numbers here. It's literally this distance, right? When we call it the width, visually, that's what we're talking about. This is the width of our class. You can see it goes from 30 all the way up to 40, basically. And the next one is going to start at 40 and go up to 50, essentially. But we don't have any overlap when we actually talk about the numbers. We don't want there to be any ambiguity. If somebody got an 89, I don't want there to be a debate whether that falls into this one, or rather, let's pick a score like 90. I don't want to know. to have any overlap. I can't say that this one is 80 to 90 and the next one's 90 to 100, because then if somebody gets exactly a 90, which category does it count towards? So we can't have any overlap in our classes, but we also can't have any gaps of possible values. So keep that in mind as well. Erase all of that. So our class width is just the difference between any two consecutive lower class limits, or we could get the same thing with the upper class limits, right? 59 minus 49 is also 10, just as 50 minus 40 is 10. So it's just the width of these bars over here. So that's what we're going to be dealing with. Okay, so we've created one histogram, and we created this histogram by basically kind of picking a predefined class width. We did it by saying, oh, I want to do it kind of by letter grades, right? And that kind of spans 10 scores. There are 10 scores that count as a B, right? Anything from an 80 to an 89, that tells me my class width should be 10. And we use that to figure out how many total classes there were going to be. If I need to span 100 possible numbers from the 0 all the way up to 99, and I want to break them into 10 or groups of size 10, which is the width that we picked, that means it's going to take 10 total classes in order to do that. So what if we have a different choice to make? What if instead of predefining how big I want the class width to be, I want to specify how many classes to use? So we basically have control over only one of these two things. If I pick how big each class is going to be, that'll determine how many classes it'll take to kind of cover our entire span of numbers that we're interested in. Or I could say, I want there to be 6 classes, and I can use that to determine how big I need to make the classes so that they can still cover that same span of numbers. So we only have control over one of those two things, either the class width or the number of classes. Once you pick one, it kind of predetermines what the other one should be. So we just did one where we picked the class width, and that determined that we wound up needing 10 classes to cover all the numbers. I want to do a different example where we pick the number of classes and use that to determine what the class width should be. So what I'm saying is, what if we want to pick the number of classes instead of the width of classes? So the way that we'll do that is sort of a two-step process. The step one would be basically approximate the class width. So approximate the class width. And we would do this by the following. So let me just say this. The class width, I'm going to give a formula, is going to be approximately. So the squiggly equal sign means approximately equal to. And all we have to do is take the largest value in our data set and subtract off the smallest value in our data set. And then we divide by the desired number of classes that we picked ahead of time. And this will give us an approximate class width. Once we've got the approximate class width, what we should typically do is round up to a nice number. Okay, so let's look at the following example and see how this will work, what I mean by this. I'm going to write out a big long list of numbers that we can use for this particular problem. So consider this list of numbers. We've got a 6, a 22, 84, 38, 41, 19. Bear with me here, there's a lot more numbers coming. 27, 63, 28, 52, 45, 41, 37, 53, 15, 28, 39, 48, 47, 33, 28, 9, 60, and 71. We'll say this is our list of numbers, and we want to create a histogram ultimately for this. And we want to create a histogram with 6 bars, meaning we want 6 classes. So create a histogram with 6 bars, meaning 6 classes. Right? Each class gets one bar. Hopefully these aren't exam scores because I see a couple single digits. And the highest score or highest number I see in this list is an 84. Maybe this is ages. Maybe it's something to do with age. We're keeping track of ages of, I have no idea, some sample that we took, and we're interested in their ages. How would we set this up? So we've picked our number of classes to be 6. The next step is to create our class width. So step 1 is to find the approximate class width. And our approximate class width in this case is going to be equal to, let me just zoom out a little bit so we can see the formula. The approximate class width is that formula right above, which says I need to take the largest value minus the smallest value. If I search through it, this is my largest value. Do that in another color. This is my largest value, and my smallest value is right here. Easy enough to spot. So my approximate class width is going to be the largest value, 84, minus the smallest value, 6, and then I'm dividing by the number of classes that we desired, which was also the 6 that we picked here. So this 6 is this 6. This 6 is the same as the one over here on our list, the smallest value, and this 84 is, again, the largest value on the list. So that's where each of those numbers came from. If you're doing this on a calculator, I'd recommend tossing some parentheses around this to make it a little bit easier. And you can do this as 84 minus 6 divided by 6, kind of all in one line with those parentheses. Or you can do it in 2 steps. 84 minus 6 is going to be 78. Divide that by 6, and we wind up with, in this case, 13. But 13 is not a very nice number to use. It's a weird number. And in fact, if this age had just been off by 1, if it had been 83 instead of an 84, we wouldn't have even gotten a whole number here. We would have had 83 minus 6, which would be 77 divided by 6, and we would have gotten 12 point something. I don't even know what that number would have been. Clearly, we are going to need to round. I don't want to use 13. So what's a reasonable number to use? Maybe 15 would be a good one. Maybe some people would choose to round all the way up to 20. In my case, I'm going to round up. That's going to be my step 2. I'm going to round this up to 15. And by doing this, it gives me some freedom. So I want to think about, and hopefully this will make sense to some people, I want to think about exactly what this would look like. If I used 13 exactly, and we've got 6 total classes, and each one's going to be of width 13. If I multiply those back together, I get back to the 78 that we had up here, right? It's the number we had before I divided by 6. So I'm saying if I multiply back by the 6, we would get 78 back. So 13 times 6 would be 78. That is the biggest span of numbers that my histogram would be able to capture if I use 13. If I've got 6 groups, and each group can contain up to 13 values, then 6 times 13 gives me a span of 78 total numbers I could cover. it would barely be enough to get us from the 6 up to the 84. By rounding up to a nice number instead of down, so if I'd rounded down to 10 instead, for example, if I rounded down to 10 and I was still only wanting to have 6 classes, now the biggest span of numbers I could get would be 6 groups of only 10 numbers each, and that would only allow me to span 60 possible values, which isn't enough to encompass both the 6 and the 84. We wouldn't be able to cover our entire set of data. But by rounding up to 15, I've given myself some wiggle room. If I do 6 groups of each size 15, 6 times 15 is actually 90. I have enough room to span 90 total values, and that's definitely enough to more than cover our bases. And it makes sense. If we're including something like ages, I would rather go from like age 0 up to age 89 or age 1 up to age 90, depending on the context of what we're interested in doing, so that we have some wiggle room in case we were to add more data down the line to this whole thing. So that's kind of the idea. So we need to round up. You can never round down. It has to be up. But just pick a nice convenient number. So now I want to create my classes. We can pick which number we want to start at. I'm going to pick 0 because of the context of the problem. If I said that these are ages, so let's pick a starting number. Right, we could pick 6 to be our starting number, but that's a weird number to start with, especially if we're talking about ages. If I pick 0, that's basically, babies. Babies haven't turned a year yet. I can include those in the data set that we're dealing with. So it makes sense to pick a starting number based on the context of the problem, what the values represent. In this case, I'm going to pick 0 as my starting point. So I'm going to create my classes here and create the same kind of table that we did before with the frequency. So I'm going to create my frequency distribution. And I'm going to have my first class start at 0. And I'm picking 0 because it's close to this 6, which was the smallest number that we had. But in the context of ages, 0 makes more sense to start at than starting at 1. Because 1 would mean we were excluding newborns. We're excluding a year's worth of babies. So I'm going to start at 0. Maybe if we were talking about people, ages of people in school of some sort, maybe it does make sense to start with the age of like 5 or 6, because that's when people start kindergarten. So again, depending on the context, that'll kind of determine where you should start. So I'm going to say if this is age, if these numbers are age, then maybe 0 is a reasonable place to start, and that's what I'm going to pick. So I already know what my class width is. This is my class width. It's 15. And if I think back to the way we define the class width, it doesn't mean I should put 15 here, because we did not define class width as this number minus this number. It's not the upper class limit minus the lower class limit. It's the difference between 2 consecutive lower class limits. So this needs to be the number that's 15. This other one should not be 15, or I wouldn't have the right class width. And now I've got it set up, sorry. There we go. Now I've got it set up that these 2 consecutive lower class limits differ by 15, and it'll give me the class width that I'm looking for. So again, remember, this is the difference that gives me the class width that I'm looking for. And it'll go up to some number. And then what should the next number be? Well, all of my classes have to have the same width, so I'm basically just counting by 15. 0 to 15. Add 15 more to that, and I would be at 30. Add 15 more to that, and I would be at 45. Add 15 more to that, I'd be at 60. I'm up to 1, 2, 3, 4, 5 lower class limits, so I need one more because we want 6 total classes. So the last one will be 75. So I've got all of my lower class limits listed out. What should the upper class limits be? Well, again, I don't want this to be a 15 because that would create ambiguity. If the number 15 showed up in this list, as it does, Which would I count it towards? Would I count it towards this group or this group? We can't have an overlap. So instead, I'm going to put the number 14 because I also don't want any gaps. I can't go from 0 to 10 and then have a gap where I don't know where I should include 11, 12, 13, and 14. I don't know which one they would go in. So we need to have our classes basically touch each other without any gaps between them, but we also can't have any overlap. So the first one will go from 0 to 14. The next one will go from 15 up to some number that needs to be close to this one, but leave it so there's no overlap and no gap. That's going to be 29. These have a difference of 15, the same width that we were hoping for. And you can kind of spot the pattern. The next number that we'll get to will be 44, and then it'll be 59, and you can see the pattern. Here it was 0, 5, 0, 5, 0, 5. Here it's going to be 4, 9, 4, 9 as the last numbers. So this will go up to 74. The last one would go to 89. So there are my classes. I now have 6 classes. We can count them. 1, 2, 3, 4, 5, 6. With an appropriate width that allows me to span from 6 all the way up to 84 with a little bit of wiggle room. And now we can go through and actually count the frequency. I'm going to do it kind of manually by hand, and I'll try to give you some hints for easier ways to do this because you're going to have to do this on the homework in this section. So first though, let's just do it by hand the hard way, just as a worst case scenario, something you can fall back on. So I want to go through this list and look for any numbers between 0 and 14. So if I go through this list looking for all the numbers between 0 and 14, I see that there are, and I'm going to cross them off as we go. Let me get a color to cross them off with. Let's do green because I haven't used that yet. So we've got the 6. The next number I see between 0 and 14 is the 9. Did I miss any? I think we got them. So that means there were 2 numbers between 0 and 14. Now I'm going to go and look for numbers between 15 and 29. So here's one number between it. So 1, going through, 2, 3, 4, 5, 6, 7. I counted 7. Oops, do that in black. That did not work. 7. Hopefully I'm not missing any. Next, I want to go for the numbers between 30 and 44. So we've got 1, 2, 3, 4, 5, 6. Counted 6. Hopefully I'm not missing any here. Go through again. Now I'm looking for numbers between 45 and 59. So 45 and 59, I'm going to do, here's the first one, 1, 2, 3, 4, 5. I counted 5 of them. Now 60 to 74. As we cross these out, we narrow it down, so there's fewer to look at. So again, 60 to 74, we've got 1, 2, and 3. I see 3 of them. And 75 to 89, I only see one number left that I haven't crossed off yet. It's that 84 right there. And so we only had one of those. And you can see this is an easy thing to screw up as you're crossing these things off a list. One thing we can do to kind of double check our work, it doesn't guarantee that we didn't make a mistake, but it's definitely, we'll notice if these numbers don't add up right, we must have made a mistake, is I can check the total. How many numbers should I expect to see? These need to add up to the total number of numbers that were in that list. And if I look at that list, it was 6 numbers across, 4 numbers down. So 6 times 4 means there were 24 total numbers in that list. So these better add up to 24, or I definitely must have missed something. So let me check that really quickly. So 2 plus 7 is 9. I'm going to add 6 to that. That gives me 15. Plus 5 more is 20. Plus 3 is 23. Plus 1 more is indeed 24. So I didn't miss any numbers, at least. My total is correct. So this is what the frequency looks like. I'm pretty sure I got these numbers right. An easier way to do problems like this, because you're going to have some on the homework, is notice that they will say that you can, sorry, what am I trying to say? It tells you in the homework that you can, underneath each one of these sets of numbers that you'll see, it says that you can download file to Excel or something like that, open in Excel. I don't remember the exact wording. But basically, if you click on that link, it will take that data set and open it in a Microsoft Excel file. And everybody has access to Microsoft Excel through our Office 365 subscriptions through CNM. So if you just log into Office 365 with your CNM email and password, you will have access to Microsoft Excel, and you can sort the data there in a really nice way. And once this data is sorted, it's a lot easier to go through and make sure that we don't accidentally miss any numbers. So I would highly recommend sorting the data for these problems. You can do it in Excel. And maybe I'll whip up a quick video that I will add in that shows you how to sort numbers in Excel. And you can also do it if you have a graphing calculator. You can do it on a TI, whatever, TI 83, TI 84. The problem with this is you have to manually type all the numbers into the calculator. And so this is possible, but it's not something I would recommend doing. So I will show you guys in another video how to sort data in Excel. So keep an eye out for that video. Otherwise, I want to move on to some other topics that are kind of important. I want to go over some terminology, and this terminology is going to be important in how we deal with all of this stuff. So I want to be able to describe the shapes of these data sets that we get. So I mentioned a minute ago, we'd looked at that histogram, and you could do a histogram for this one as well. I'm not going to bother to draw out the histogram for this data set. You would do it in the same way we did the other one. But if we want to look at a data set and create the histogram, I want to be able to describe the shape of the histogram. So this is basically some terminology that you'll hear me use, and it's important to know what I'm talking about when I say these things. So terminology specifically for histograms or for the shapes of our data. Okay, so let me get a couple axes here. And I'm just going to draw some shapes. I'm not going to label these ones carefully. Just want to kind of get the shape of the data and give you some words that go with them. So if you have a data set that looks something like this, how does that compare to one that looks something like this? Or one that looks like this? Again, you'll bear with me here, hopefully. So just looking at them, it's clear that these are all totally different shapes. How do we describe these? Well, this first one will be what we referred to as skewed, and the direction that it's going to be skewed is to the right. The next one is also skewed. You can tell it's skewed in the opposite direction. It's skewed left. And the last one doesn't appear to be skewed at all, and this is what we would refer to as symmetric. So we have a symmetric histogram, we have one that's skewed right and one that's skewed left. This can sometimes be counterintuitive for some people. Notice on this one, most of the data is actually over here to the left. So why don't we say it's skewed left? Well, it turns out when we talk about skew, we're interested in where the tail of our data is. And this is what I call the tail of the data. This is the tail of the data. Wherever it kind of trails off and has a little bit of data, but not very much, that's kind of where we would consider the tail. This has two tails, right? One on this side, one on this side. That's what makes it symmetric. But these ones have tails that kind of only are on one side. And visually, that's what we're kind of looking for. It could have two tails, but maybe if one tail, for example, I'll erase this in a minute, but if this tail over here carried on a lot further in this direction, you would say the same thing. This is no longer symmetric. Now this one is skewed to the right because the tail on this side is so much longer than the tail on this side. So just keep that in mind. That is the way that we, did I give them all? Yes. That's the terminology that we're going to use for this, skewed left and skewed right. We'll also talk about how many basically bumps there are in our graph, how many humps. So we might have something that looks like this. Versus something that looks like this. So here are our two different data sets. And in this case, again, I'm talking about the humps, the peaks. You can see that this one only has one peak, whereas this one has two peaks that are the same height. If you think of them as sort of mountain peaks. We're going to drop the word peak and instead use the technical word that we're actually going to use in statistics, which is a mode. And if you've heard of the mean, median, and mode, this is that same mode as in a mean, median, and mode. It's the most frequent value that occurs, right? It's going to be whatever value is we have down here. That's the most frequent one that occurs. This one has two. So if we have one mode versus two modes, the terminology that we'll use is that it's either unimodal, if it only has one, like a unicycle only has one wheel, versus, if we're on using that same comparison, a bimodal. So bimodal has two peaks, unimodal has one. Technically, you could go on and say something is trimodal if there's a third peak, but we're not going to really worry a lot about that. It's not something that's going to be super, super important. One other quick concept that I just want to sneak in before we're done with this video is something called a cumulative frequency distribution, or cumulative frequency. And if I cheat and go back to the example we did before that I've got right here, if this is the data that I want to use, so let's imagine that I've got that same data set. I'm going to copy it down right here. In fact, let me see if I can do that with this. I want to copy the whole thing. Okay, so I've just copied it down here. Imagine I want to create the cumulative frequency. The cumulative frequency is just going to be what we would get if instead of asking between 0 and 14 and seeing that there's 2, and then in between 15 and 29 and seeing that there's 7, as we accumulate, we just want to accumulate the contents of each class as we go. So for this category, we're still looking at 0 to 14, and there's still going to be 2. But by the time I get down here, the question isn't how many are between 15 and 29. The question is how many are between 0 and 29. So I want to start at this number for all of them. So for the first one, it was from 0 to here, and there were still just 2. Next one, it's going to be from 0 all the way down to here, and that's the 2 that were up in this class plus the 7 that were in this class. I have to add those together. It's 2 plus 7, which gives me 9 total. For the next one, it's going to be from 0 all the way up to the 44, which is going to be the 2 that were in this class, the 7 that were in this class, and then the 6 additional that were in this class. So I already added these up and got 9 out of them, and I just need to add that additional 6. So that gives me 15. For the next category, it would be from 0 all the way up to the 59, which is the 15 I've accounted for between the first 3 classes plus 5 additional. So it would be 15 plus 5 more to give me a grand total of 20. The next one I need to go from 0 all the way up to 74, which is the 20 I've already accounted for up to here, plus 3 more from this class, so we'd be at 23. And lastly, from 0 all the way up to 89, we've now covered all the values in here, and we've added them all up. We take that 23, we just add this one last one that was unaccounted for, and we're up to 24. This number should always match our total here. They need to match. But this list of numbers is what we call the cumulative frequency. And it can sometimes be a useful thing. We'll use the idea of sort of a cumulative set of numbers later on in the course, but I just want you to become familiar with this term now. And keep in mind that as we do a cumulative frequency, by the time we get to the bottom, the biggest number that we get in our cumulative frequency should match the total. It should be the sum of everybody should have been accounted for at that point, and it should match the total number of observations that we looked at.